that other teachers do not even consider doing.
You're welcome. Yes. Okay, so once again, we're on 12.1, number 30. It is the bowling ball problem. It has 3 stars next to it. Hello, this is Mr. Hecker. Willard is out today. Govind is out today. Yep. Yep. Bye.
I still think I should
All the smart kids like smoke crack or something.
No. This is our being recorded.
Mr. Hecker, I heard you're getting your tattoo colored soon.
That is exciting.
Yeah, a week from Wednesday. I am excited. Yes.
Wait, why are you going to take your next week again?
It's a conference for
Conference for later, yeah. Okay, so here we go. We are doing number 30. It is the many-starred bowling ball problem. So what we had decided yesterday was that as the bowling ball rolls, there are going to be 2 effects of friction, right? So there's going to be, gravity and normal force. Those are not going to affect the motion either linearly or angularly. Is everybody okay with that? All right, so in terms of force, what we're going to have is this. You're going to have the force of friction pulling it backwards. So when we write our net force equals net force equation, we're going to have not quite enough room to write the equation. We're going to have that the mass of the bowling ball times the acceleration of the bowling ball is equal to the force of friction. Yes? Okay? Now, in terms of torque, what we're going to have is this. Here's our bowling ball. Here's the center of the bowling ball. Because friction is pulling the bowling ball backwards, that's going to provide a torque. So if we do net torque equals net torque, we're going to have the rotational inertia of the bowling ball times alpha equals the torque provided by friction, which is the force of friction times radius. So let me pause there for 1 minute. Does all of that make sense?
Yeah.
Now, can I, at the beginning of the problem, when the problem first starts, can I use a jumper to replace alpha with A over R? No, because it is not smooth rolling yet, right? So those jumpers only apply once the smooth rolling begins, all right? So I can't use the, so to be clear, this is the acceleration of the center of mass. So I can't use this. Let me highlight to call attention to it. These 2 things here are only true if smooth rolling. I need to apologize to Mrs. Moreland, whom I yelled at on the telephone. I am now self-conscious about that. All right. I should also apologize to the smartboard, yes, for throwing a marker at it. Okay, is everybody good up to here? All right, so this is kind of our setup. Now, the problem, if I remember correctly, gives us a little more guidance than just here, solve this. So let's see what it says. Part A says, well, okay, so you got to read the sentence before Part A. So right before Part A, it says, when the speed v of the center of mass has decreased enough and angular speed has increased enough, the ball stops sliding and then rolls smoothly. That was what we kind of talked about yesterday. Did that idea make sense?
Yes.
All right. So A says what then, meaning at that instant, is the velocity of the center of mass in terms of omega. So this right here is, that's part A, right? Cool. B, during the sliding, what is the ball's linear acceleration? Let's see. What else do we know here? Oh, we know our coefficient of friction, don't we? The problem tells us that the coefficient of kinetic friction is 0.21. So I can go back up here and add in some information. So let's see. So my gravity is going to be mg. Notice where I drew my force of gravity from, right? What's my normal force going to be? mg, right? Enough to cancel it. At what? Remember, now we got to be specific, not just about how much force and what direction it points in, but At what point on the object does it act? Point of contact is where my normal force occurs, right? And that's also equal to mg. Oh, well that means my friction then is just the coefficient times that, right? So my force of friction is, holy moly, my board is getting all cluttered, 0.21 mg, right? Good or no? Cool? Congratulations, Hannah.
Thank you.
I don't know what that's for, but all right. I appreciate your positive support. Okay, so here we go. So let's solve this thing. So let's see. So we've got mass times the acceleration of the center of mass. That's got to equal our force of friction. Well, that's 0.21 times mg. M's cancel. Oh, I said M's cancel. And so the acceleration of our center of mass is whatever 0.21 times 9.8 is. I happen to have a calculator right here, and it knows the answer to that question. Gives you, thanks, Thomas. Gives you 2.058 meters per second squared. Sorta. Why sorta?
It's negative.
It's negative, right? You're losing velocity, right? Because the friction's working against the forward motion. Cool? All right, so that is part B. So this is how quickly the bowling ball is going to lose speed as a result of friction. C says during the sliding, what is the ball's angular acceleration? So this was B. C, we got to go over here, right? So here we go. So let's see, I for the bowling ball, that is 2/5 times the mass of the bowling ball times r squared, right? Times alpha equals the force of friction, which is 0.21 mg times r. Do we know the radius?
Yes.
We do! Oh, good. I was nervous because they don't cancel here, right? Very often they do cancel, which is why I hadn't even written it out yet. I just had assumed, starting the problem, that the radius, yeah, there was one radius. I was going to assume that the radius would cancel everywhere, but it doesn't. So we got to plug in our radius. Are there any problems with what I've got here? To be clear, I've been really sloppy here, alternating between capital R and lowercase r, which is terrible. They're meant to be the same thing for this problem, so I apologize if that's confusing. Weston, and then Sean.
Are you picking the contact point to be like the floor? Is that why the wouldn't the force of gravity have torque though, because it comes from the center?
Yes, but it's perpendicular to your lever arm. Let me draw that so you can see what I'm talking about. So if this is the floor and this is the ball, I'm drawing this in green. Here's my contact point. My force of gravity is here. Force of gravity is directed down through the point of contact. Your lever arm goes from the point of contact to the center. So the angle between them is either 0 or 180. I guess technically it's 180, but the sine of 180 is 0. Does that make sense? Everybody good with that? Cool. I apologize if I glossed over that. Okay. Oh, Sean, you also had a question.
I just have a question, a simple question about like just general math. How come one radii is a radius,
I don't
like multiple
I don't
radii?
know. We can have it on later. Talk about it later. I don't know. There's lots of weird things grammar-wise. Okay, so M's cancel. One of the R's cancel. Sorry, Sean, not playing today.
Okay.
Too much to do.
I respect.
Oh no. Okay. Come on, you stupid computer.
It's trying its best.
It's magic.
That's exactly what it is. Go away! There we go. Okay. So let's see. So we can plug in our numbers here, right? So we've got 2/5. The radius is 11 centimeters. Is that right? You giggling about did something happen? 11 centimeters times alpha equals 0.21 times 9.8, right? And solve for alpha. Yeah?
Well, is there ever a time where the normal force will have a torque and the force of gravity won't, or if one doesn't have a torque, the other one therefore won't either? Is that?
Yeah, I mean, they don't. Let me finish this and we'll come back to that, okay? Because it's a good question that we should explore, but let's one thing at a time. Okay, so let's solve this mess. So I'm going to get that times 5 divided by 2 divided by 0.11 gives you 46.8. Is that right? Based on your lack of a response, I will assume that I'm good. Okay, so everybody cool up to here? Hey, ooh, you rule. Do you guys know Mr. McGuire? This is what he looks like. He's got a fun green Lucky Charms shirt because St. Patrick's Day is coming up.
Yes. Yeah, no, it is.
He's Irish.
Here, I brought you 2 balls.
Thank you, I will. Sean, that was for you. Okay. All right. All right. So is everybody good with B and C? All right. Now, to be clear, I want to make sure you guys understand this. The linear acceleration is causing the linear velocity to decrease, right? The angular acceleration is causing the angular velocity to increase. And again, the whole idea is when this equals that, smooth rolling. Hooray. Okay, so that's A, B, and C. Are there any questions? Okay. C says, how long does the ball slide? So here it really makes a big jump. So we're trying to find time, right? And the issue, so we just found 2 different accelerations, acceleratii, if you prefer. And we're trying to figure out when these 2 things are equal. So I feel like we should start with this equation and see if we can write an expression that deals with this with respect to time. Follow?
Oh wait, you need. Okay.
So in other words, we know our acceleration of our center of mass, right? So let's see if we can write an expression that tells us the velocity of the center of mass as a function of time. So this is an equation from last year, right? And I unfortunately have not written it on the board today, but what was the initial velocity of the ball? Initial angular velocity 0. Initial linear is 8.5. So the velocity of our center of mass should be VI plus A times T.
That's VF.
Yes. So this is the velocity of the center of mass as a function of time. So yeah, it's VF. F as in at the end of some amount of time. Cool? All right, now let's do the same thing over here for our angular motion. Oh my gosh. I don't know why the smartboard hates me today. I do know why. I threw a marker at it. We've resolved that. Okay, so here we go. Let's write an expression now for the angular velocity as a function of time. This one? What do you need, Jack? Okay. Are you sure?
Yeah.
You can speak up. You can say, hey, hacker, slow down. I don't know what you're doing. You can move up. Here's an empty seat right here by John. All right. So omega is, there you go. Omega is alpha t, right? So 46.8 times t, right? So now what do I do? Sorry, I lost you. What happened? How did I get this?
Yeah, you just use the
Oops. No, it's final velocity equals alpha times t plus initial velocity. And the initial angular velocity is 0. Good, you guys? Weston, you good?
Yeah, it's just like you think you'd write a consistent, like, you have, never mind. And fine.
You sure?
Yeah.
Okay. Okay.
You have it, never mind.
Okay, so now I can set v equal to omega r, right? So here we go. Jack, you good? Good. It's nice to see you. Equals omega, which is this, 46.8 t times r. And then solve for t, and then the rest of the problem kind of falls apart, I think, right? R.
Wow. So,
All right. So does that make sense? So now we have an equation. We can solve for time. The next question says, how far does it go? So you use your linear values. Once you get your time, you can find the linear speed of the ball. So I think once you get to here, that's kind of the deal. Cool, you guys, or no? All right. All right, so I try really hard to make sure it's not just, here's how you solve that one problem. What's the lesson? What's the whole point of all this BS? We did a whole bunch of stuff here. What does it all mean?
Just from sliding to smooth rolling when the center mass equals, oh my god.
Good. If you've got an object that is not smooth rolling, it will begin smooth rolling once your jumper equations work for the center mass. Okay? And vice versa, right? I think somebody had asked about what if it stops smooth rolling? Well, when it stops smooth rolling, you lose these guys, right? If you had an object that was rolling and then it suddenly came on a frictionless surface, it would I guess, shoot, I guess it would actually end up being the same thing, right? Because
The other way around. But wouldn't the velocity and the angular velocity just be constant?
yeah, I guess they would. So it wouldn't matter.
What if you started on like a friction of like an AC patch and then you pushed it and then it came off that?
Right. Well, that's what this is, right?
Oh, is that how? Yeah.
So yeah, I guess you're right. Okay. Anyway, are we good with this?
I'm great.
Awesome sauce. All right, let's move on.
Wait, when you solve for like you use the two separate equations to get like the different like acceleration, angular, and linear.
This guy
At the
down
same time,
here.
What do you do with like the v center of mass equals omega r once you like do all that stuff?
Solve for t.
Yeah, but you already solved for t using the two accelerations, the linear and angular. You didn't solve for t using v center of mass equals omega.
No, I mean solve, like numerically solve for t. Right now I've got an equation, and my only unknown is t. So if I solve this equation, what I'm doing is I'm figuring out at what time this becomes true.
Oh, okay. I like get that part. I just thought the v center mass equals omega r was more important.
It is important. That's how I wrote this equation, because the left side of this equation is the v, and the right side is the omega r.
Oh.
Do you know what I mean? So what I did was, again, over here I wrote an expression for v at some time. Over here I wrote an expression for omega at some time. And then I plugged them both in to v equals omega r to find out at what time that became true.
Okay. I follow.
You good? I know, it's a tough problem. There's a lot going on. That's why there are 3 stars on each side of it. A total of 6 stars. It's a lot of stars. I think it's more stars than I've ever put on a problem. All right, are we good? Okay. Yesterday, I didn't get a great sense for kind of what you guys wanted to look at. Are there other problems that jump out at you guys? I feel like, so here, let me say this. So 32, the yo-yo problem, is very similar to 31, the massless axle problem that we did yesterday. In fact, it's almost the exact same thing. So if you struggled with 32, look at what we did with 31 and go back and try it again. Other good ones to do, I really like 27. That's a pretty straightforward application of net force equals net force, net torque equals net torque. So that's a good one. I'm not ignoring you, Weston, I'm just looking. I'll get you in one more second. The ball in the loop problem is a good one. I don't know, what were you going to ask? Question?
You said you'd explore why my torque thing with the
Oh, yeah. So your question was...
like if like net force doesn't do work or force of gravity, therefore not produce torque either, my bad.
No, there's no connection between the two because, for example, if you've got... suppose you've got a block on an inclined plane and maybe there's a little peg here or something to prevent it from sliding down. Then your normal force is going to be perpendicular to your lever arm, so the normal force exerts no torque. Follow? Where, I don't know, I didn't draw that all the way down. Whereas your force of gravity is not perpendicular, so your force of gravity there would produce torque.
Okay. It just so happens that if they're both true in a rolling object.
It's more because the surface is horizontal than the fact that it's rolling.
Okay.
Cool?
Yeah.
In fact, if I made this into a rolling object, and I consider this as my pivot point, the normal force doesn't provide torque, but the parallel component of gravity does. That was one of the ways we explained why something rolls downhill.
But do you never care about the perpendicular?
Tell me why.
Oh. It's the angle between the two. It's going to be 180.
Follow?
Oh, I was thinking that you picked the contact point to be like but I guess it acts on the center of mass.
Yeah, your gravity acts on the center of mass.
Okay.
Yeah. Good, you guys? Okay. How did you guys do with number 27? It's called the force on axle problem. That's a good one to do. There was one similar to this on last year's test. So that's a good one to do. How did we do with it?
What's the answer?
Some sort of
26?
feedback. 27
Yeah.
was good.
Wait.
Confused on B. Rotational inertia.
Oh, I'm looking at the wrong question.
Okay, so you're okay?
Yeah.
Question?
For 28, when you're solving for B, I don't understand what you. It reminded me of like this.
When you say when you're solving for B, do you mean part B of the question?
Yeah.
Okay.
Like I wasn't solving like you did like this whole thing of like, what if the object isn't at the top or bottom of the circular path? You like the inward force would be equal to like the, or is that just only if like there's like this? I'm thinking like the Spider-Man on the ride. Remember?
Yes.
It's different.
I
It's
do.
like I'm wondering why you don't care about like the force of gravity when you're
Are
calculating.
you talking about part A?
No, part B.
Or B?
Because he's at like that. He's not at the top or bottom.
Yeah, but yeah, so yeah, but he's at a point that is. So for what is this? 28B. You've got this loop, which is a circle. It's got a radius R. Sorry, capital R. Over here at point Q, there's two forces. I guess three really, because there's some friction. But so, what's the magnitude and direction of the horizontal force component acting on the ball at Q? So, I mean, what's important about that horizontal component of the force? Yeah, it's your centripetal force, right? So that's, I mean, the idea is find the velocity at that point, and then do mv squared over r, and you're done. So maybe I don't understand what you're asking.
Yeah.
It would have been much more difficult if I'd said here or here.
That's
Okay, but here because it's, horizontal from the radius.
So would you have to break centripetal up if there were out there to force of gravity?
At one of these points, yeah, it gets ugly.
Okay.
Yes.
So for 26, that was the one that like told you, I don't know what it was, but
Hold that thought for 1 second. This is not me being dismissive. But while we're talking about 28 ball on a loop problem, were there any other issues with this one? Weston, do you understand what I was saying there? That the centripetal force is is the horizontal
Right.
force?
Yeah. Because then you have like horizontal and vertical components, and then the horizontal ends up being centripetal, and the vertical, yeah. Like the centripetal force ends up being the summation of the force gravity.
Well, here your gravity pulls down, so that doesn't contribute to the centripetal force, right?
Yeah. I'm talking about when it's at the one of the
Yeah, right. At one of the correct. Yeah. Okay, John, what do you got?
So for 26, I was confused when it said like 1% is RKE of like your total kinetic energy. It's like, why wouldn't it just be like
1/2 I omega squared over like the 1 plus beta times 1.
Really good question. So the car is rolling, but the car isn't rolling,
Uh,
just the wheels are rolling.
so when I do total energy, is it like 1/2 times the mass of the car times its velocity plus the rotational kinetic energy of all two?
Correct. Does that make sense?
It's the
And there's a
massive.
couple ways of doing that, but yes, what you just said conceptually is right. What's up?
It's the mass of all of it because the wheels have kinetic energy too.
Yes, so when you're doing your kinetic energy, the body has kinetic energy and the wheels have kinetic energy.
And then
But when you do
just,
rotational kinetic energy, it's just the wheels. Good?
So you only use that equation when the object you're finding out which is the thing rolling?
Correct. When all of the mass is rolling. Cool, you guys? All right. Anything else jumping out at you guys on this? Okay. Cool. So, I told you guys yesterday that we would go over the rest of this today. I don't think I made it explicitly clear whether I wanted 12.2 do or not. So I don't think it makes sense to go over that now. So I'm going to shut up. I'll go around and answer individual questions. You guys have got time to work, I guess, unless you guys have something else you'd rather see, rather do at the time. Please, please, please. I'm out for 3 days. This is not ideal. You guys need to be using the time. First priority should be working on the chapter 12 stuff. Okay, finish up 12.2 and 12.3. 12.2 is basically the angular counterpart to that's basically 12.2. It's okay. Or if your torque isn't constant, then so that's 12.2 in 1 minute. All right. And then 12.3 is conservation of angular momentum. That's why when a figure skater spins and pulls his or her arms in, they spin faster. Okay. I think of the concepts, that's probably the easier one. So anyway, do the best you can with that. I posted last year's test. I will try over the weekend to post the solutions to it also. So Thursday and Friday will be Q&A for chapter 12 stuff, test Monday. All right? My assumption is there's going to be some stuff on chapter 12 you're stuck on. Fine. Do as much as you can and then move on and try to start chapter 13. Chapter 13 is just one video. It's equilibrium. Okay? It's net torque equals 0. Okay? Same thing. Try some of the problems. We will use Tuesday, Wednesday, Thursday next week to answer questions about chapter 13. But if you leave it until after the chapter 12 test, you're going to be effed. I'm still recording. Hello, everybody. So my point is use the time wisely next week. Help each other. Work productively. Clear? All right. I'm sorry. I know it's not ideal, but we got to keep moving. Okay? Follow? I don't remember. It's somebody that I've had before. I don't remember what her name is. Corey? Is that the name of a sub? For some reason, that's ringing a bell with me.